So this is our NZ graph. This is our NZ graph. You can see that along this x-axis we have plotted number of protons, and along y-axis we have plotted the number of neutrons. Okay, and this region is called zone of stability, within which we have. So these are the number of protons and number of neutrons for stable nuclei. Okay, stable isotopes. Okay, so the straight line is the line for n equals to z line, where neutron into proton ratio is 1:1. For z, and this red region, whether this is a straight line or some broad region, this shows the zone of stability. So within this region, all those nuclei lie which are stable. Okay, so for proton number less or equals to 20, okay, number of protons less or equals to 20, all the isotopes, stable isotope, lie along this red line, which is along the n equals to z line. Okay, so for z less or equals to 20, atomic number less than 20 or equal to 20, the stability line is equals to z equals to n equals to z straight line. It implies that only those nuclei are stable. Okay, that is the lighter nuclei. Atomic number less than 20 means the lighter nuclei are stable, which have equal number of neutron and protons. Okay, so if you pick any nuclei here, you will find that they have equal number of neutron and proton. Okay, so for lighter nuclei which have less than 20 protons in them, only those will be stable which have equal number of protons and neutrons in them. Now what happens when proton number increases, become greater than 20? As the proton number increases, become greater than 20, we see that this zone of stability bends upwards. It means that, so here if you pick any stable isotope, you will find that it has a greater number of neutron than the number of proton. It means that as proton number becomes greater than 20, only those nuclei will be stable which have greater number of neutrons in them compared to their proton number. So here along this line, n:p ratio, that is neutron into proton ratio, is no longer 1:1, but neutron to proton ratio becomes greater than 1. Okay, so why this happens? Because as proton number increases, the proton number 1 becomes greater than 20. So the number of protons in the nucleus increases. As a result, we know the positively charged protons are repelling each other due to Coulomb electrostatic force. So as the proton number increases, the Coulomb electrostatic repulsive force becomes very dominant. So the protons try to move away, they were repelling each other, which decreases stability of the nucleus. The nucleus tend to become more unstable. Now to compensate for this factor, we need to increase the stability. Okay, so now there has to be greater number of neutrons to compensate this repulsive effect. So now if we add more neutrons to those nuclei, what happens? The nuclear force become more dominant. It becomes more effective than the repulsive force. The attractive nuclear force becomes more dominant than the repulsive electrostatic force. So the nucleus again become stable. So that's why as proton number increases, there has to be greater number of neutrons in the nucleus to increase the effect of the attractive nuclear force, so that the nucleus become stable. So we can say that as number of protons or atomic number increases, the more number of neutrons are added to the nucleus to keep the nucleus stable. So around this region, so this is the zone of stability, as we have seen. Within this region, there will be all those stable isotopes which have their neutrons, a number of neutrons, where the number of neutrons will be greater than number of protons. But this is applicable for the medium weight and heavier nuclei. Okay, so around this region, around where the number of proton is 40, we'll find that n:p ratio Okay, like n is to z ratio along this line, or for the lighter nuclei it is 1 is to 1, but here this neutron is to proton ratio will be around 1.25 into 1. So as you can see that the proton and neutron into proton ratio gradually increases, and then again around where the proton number is 50, the neutron number you will here in this region. So if the proton number is 50, then the stable isotope will lie in this region. So in this case you will find that the neutron is to proton ratio will become 1 is to 4 is to 1. So you can see that as gradually proton number increases, the number of neutrons in those nuclei also increasing to keep the stability, and becomes greater than that number of protons. For example, the heaviest stable isotope, which is bismuth, has neutron is to proton ratio as 1.518 is to 1. So this is the zone of stability. Okay. Now if an isotope lies above in this region, left side of the zone of stability, or you can say the left above the zone of stability, it is unstable, and all those nuclei which lies below the zone of stability or to the right side of the zone of stability are also unstable. Okay. So if an isotope their proton number and neutron number ratio is somewhat here, okay, they are unstable, that is radioactive, and they become stable by beta minus emission. Okay, that is electron emission from the nucleus. And if those nuclei lie below the zone of stability or to the right of the zone of stability, then they are also unstable, they are radioactive, and they become stable by beta plus emission or the positron emission.